Hello everyone. Today we will present about data algorithm and design in the context of DFS versus BFS in file searching. We have already made a paper about it. Today we'll present BFS and DFS versus in file searching. Okay, next slide please. Okay, the introduction will discuss about why file searching matters. In the modern computer system store large amount of data. Files are organized in hierarchical directory structures. Searching files manually becomes inefficient as directory grow larger. Tree traversal algorithms can automate and optimize file searching. Directory structures literally form a tree. Therefore, graph traversal algorithms such as the DFS and BFS can be used to search file efficiently. Next, problem statements challenge in file searching. Large number of files and folders, deeply nested directory structures. Manual searching is time consuming. Efficient traversal algorithms are needed. As the numbers of files increases, users need a systematic way to locate files without browsing every folders manually. Next, directories as trees. This is will represent the tree in table. The tree representation. There are several components in tree, such as root, parent, child, and leaf. They will represent the root will represent main directory, parent will represent the folders, and child will represent the files or subfolder in the folder container. And leaf will represent file without header. The mm, leaf akan ada di ujung folder yang nggak memiliki anak lagi. A directory structures can be modeled as a tree where folders act as a parent nodes and files or subfolders act or child nodes. Next, this is the characteristic of BFS. Explores one branch completely before moving to another branch. Use recursion or stack. Requires less memory and suitable for deep directory structures. For example, we will traversing the folders in VirtualBox VMS. As you can see in the GMD commentary slash F, there are two folders will be traversed with oh, where each folder have the subfolders. For example, from VirtualBox VMS, they will go to Kali Linux Fund. They will go to Kali Linux Fund logs. Kali Linux Fund will backtrack to top folder snapshots. Kali Linux Fund backtrack. Kali Linux Fund backtrack. There are um, until the VirtualBox VMS the root node. After that, they will traversing the metasquare table, logs, and n. So first they will traversing the Kali Linux Fund. After they didn't found any nodes, they will backtrack to VirtualBox and traversing the metasquare table until the deepest nodes. The DFS goes as deep as possible before returning to previous folders through backtracking. Okay, next. BFS characteristic. Explore nodes level by level. Use a queue data structure. Finds the nearest target faster and requires more memory. We will have the example of same as the DFS before. For the traversal from VirtualBox, Kalinup funds, Metasploit table, Kalinup fund, the subfolder, logs, subfolder in Metasploit table, logs, subfolder in Kalinup fund, and snapshots, subfolder in Kalinup fund. So the BFS traversing from the breadth first level from Kalinup fund Metasploit table, it's the parent node at the same level and the subfolder Kalinup fund at the same level and so on until the nodes have no children again. BFS visits all nodes on the same level before moving deeper into the tree. Okay, next. This is the comparison between DFS and BFS from the features that the structure. DFS using stack or recursion. BFS using queue from the traversal. DFS using depth first and BFS using breadth first. Memory usage, DFS consuming lower memory and BFS consuming higher memory. From the search speed, DFS better from deep trees and BFS better from for shallow targets. From the backtracking, DFS is yes using backtracking, but in the other hand, BFS didn't use backtracking. The main difference is that BFS prioritizes depth while DFS prioritizes breadth. Okay, next. This slide will be present by my friend Indra. Okay, Indra.
Okay, so thank you. Alright, so now this is the technical side. It is how about how these algorithms are implemented into the Python code we built. So as we can see on the screen in the left side, the DFS algorithm purely utilize recursive characteristic. The DFS function will call itself every time it encounters a new subdirectory. And here we don't need to manually create additional data structure because the program automatically utilize the operating system within construct to store the traversal path. And meanwhile, on the right side, the BFS implementation has a very different logic because BFS must explore horizontally level by level. We are required to use a queue data structure, which in this code we implemented using the naked object. And here, every time a folder is explored, all of its children or child nodes are inserted into the queue to be processed sequentially. So, after looking at the code implementation, let's analyze the first performance parameter, which is the complexity. Based on our testing theoretical analysis, both DFS and BFS have a equivalent growth rate, which is on linear scale of ON. And why is that? Because in the worst case scenario, such as when the file being searched for is at the very end of the data structure, or even when the file is not found at all. What algorithm must fit and examine every element or not exactly once. So if a system directory has a total of 1000 files and folder, the execution times curve for both algorithm will grow proportionally to the number of elements without any redundant computation. Okay, so now if the time is the same was twice the main difference. So the most crucial and fundamental difference between these two algorithms actually lies in system memory usage or space complexity. This is where a very interesting thread of our comparison occurs. As we can observe on the chart on the screen, the FS memory usage is much more efficient and constant, denoted by OH, where the allocated memory only depends on the height or the path level of the path currently being actively explored. When the algorithm performs backtracking, memory is immediately released back. Conversely, the S memory usage has the potential to swell exponentially because it is denoted by OW, whereas the memory space allocation is directly proportional to the width of the tree structure level. DFS is forced to simultaneously store all nodes on the same level into the queue before moving to the level below it. This carries a high risk on consuming a massive amount of RAM if a single folder contains thousands of elements. So, as a conclusion and the main takeaway from our research paper, there is no single algorithm that is absolutely superior in all conditions. The effectiveness of this file search is highly determined by the characteristic and topology of the directory structure encountered. Our recommendation: use DFS if your computer system has strict memory constraints, or when you are dealing with directory structure that have very deep and complex subfolders. On the other hand, use DFS if a suspect of know that the target file is located close to the main directory or root, because BFS guarantees finding the file at the close level with a faster response times. Okay, so therefore, appropriate dictionary structure modeling combined with the selection of a suitable traversal algorithm will produce an optimal and efficient file search system. That concludes the presentation from our group regarding the implementation and comparative analysis of the FS and BFS algorithm for file searching in system directory structure. So maybe that's all explanation from our group. I close it with thank you.
Okay, thank you, Indra. This is the end of our presentation. If we say anything wrong, we will apologize. Okay, thank you. Bye bye.